Good afternoon, ladies and gentlemen. How am I coming through?
Good.
You're fine on my end.
Alrighty. Okay, well, today we are going to spend some time in the XY plane as we look at the graphs of functions, quite a few things, graphs of functions, domains and ranges of functions, X and Y intercepts, also functional notation in the last section for today. Okay, so 2.1 and 2.2. 2.1 is going to have us visit the XY plane. All right. So section 2.1. All right, what I want you to get out of this section are a couple of things. We all know how to plot ordered pairs or points in the XY plane. Is that a fair assumption? This is called the XY plane here. All right, in general, suppose that I have a linear function graphed in the XY plane. Well, hold on a second. All right, the first thing I'm going to do is develop what's called a distance formula. And this formula can be used to compute the distance between any two points in the plane. Suppose in general we have some point here, x sub 2, y sub 2. And here we have a point x sub 1, y sub 1. I'm going to show you how to compute the distance between these points in the XY plane. So to derive this formula, we can build a right triangle here. All right, and if I project this ordered pair down to the x-axis here. If I project that point vertically down to the x-axis, it would strike the x-axis at the x-coordinate of this point, which is x sub 1. In a similar way, if I project this point vertically down to the x-axis, it would strike the x-axis at x sub 2. If I project this point horizontally back to the y-axis, it would strike the y-axis at y sub 1, since that's the y-coordinate of this point. And projecting this point horizontally back to the y-axis, it would strike the y-axis here at y sub 2, because that's the y-coordinate of this point. Okay. We understand the picture so far. All right, how do we find the length of this side of our right triangle here? Well, the length is just going to be the difference between the x coordinates. So we can denote that as x sub 2 minus x sub 1. The length of this side of our right triangle is the difference in the y coordinates. That's just going to be y sub 2 minus y sub 1. And therefore, ladies and gentlemen, to find the distance between these points, I'll call D. We can make use of the fact that this is a right triangle, and we can subject its sides to the Pythagorean relationship. And this Pythagorean relationship, which is actually a theorem in plane geometry, guarantees that if I take the longest side of this right triangle, the hypotenuse, and square its length, that's going to be equal to the sum of the squares of the two shorter sides of the right triangle. And so we arrive at this relationship here. Now, to solve for the distance between these 2 points, we take the square root of both sides of this equation. And therefore, the distance between those 2 points is going to be the positive square root of the sum of the squares of the differences between the coordinates of the 2 points. This is called the distance formula here. Okay. So this formula will enable us to compute the distance between any 2 points in the XY plane. So given 2 unique points, we can compute the distance between them by using our distance formula. That's what this is called here. So I want you to be familiar with this formula. All right. Any questions with how we got that there? All right, another formula, ladies and gentlemen, is called the midpoint formula. Suppose I wanted to find the midpoint between these 2 points. That's the point halfway in between these 2 points. Well, that would be this point right here, let's say. That's your midpoint. If you project this vertically down to the x-axis, it'll strike this value right in the middle in between x of 1 and x of 2. You project this midpoint back to the horizontal axis, it'll strike a tick mark value halfway in between y sub 1 and y sub 2. So what's the average on the midpoint of x of 1 and x of 2? That's going to be x of 1 plus x of 2 divided by what, 2? And what's the halfway value between y1 and y2 here? That's going to be y1 plus y2 divided by 2. And so therefore, the ordered pair address of this midpoint is going to have an x coordinate that is the average of the x coordinates of the 2 endpoints. And the y coordinate is going to be the average of the 2 y coordinates of the endpoints. This is called your midpoint formula. It enables you to find the midpoint halfway in between any 2 points in the XY plane. So the distance formula and the midpoint formula. All right, so those are 2 important formulas out of section 2.1 that I want you to be familiar with here. And why don't we apply those formulas to a problem, okay, and see how they actually work. Okay? Any questions here on this page here? All right, well, let's see how we can actually put those into action here. So suppose that we're given 2 points in the XY plane, -1, -3, and the ordered pair 3, -7. And in question A, suppose I want to compute the distance between these points. And in question B, suppose I want to find the midpoint of these 2 points. All right, now we need to label these points as which one's our first and second point, and it doesn't really matter which one you call your first or second point. It's just a matter of choice. So we'll call maybe this our first point, x1, y1, and we'll designate this as 1b and x2, y2. Okay. All right, so for part A, to find the distance between these 2 points, we use the distance formula, which we take the difference between the x coordinates, square that, and add it to the square of the difference between the y coordinates. So the distance between those 2 points, we feed things into the distance formula. My x sub 2 here is going to be 3, based on how I labeled my points, minus x sub 1 is -1. Y sub 2 is going to be -7. Minus y sub 1 is -3. Just be careful of your signs when using this distance formula here. So going through and doing the arithmetic now, 3 subtract a -1 is 3 plus 1 or 4. 7 subtract a -3 is 7. -7 rather subtract a -3 is -7 plus 3, which is a -4. And hence it looks like our distance is going to be 16 plus the square root of 16 plus 16, or the square root of 32. That would be the distance between these 2 points in the XY plane. And the square root of 32 can be simplified as 32 is rewritable as a 16 times 2. And the square root of 16 brings a 16 out as a 4. So we would say that the simplified distance between these 2 points is 4 times the square root of 2 units. That's the distance between those points. Any questions how I computed the distance between those 2 points in the XY plane? What would be the midpoint? The point that's halfway in between these 2 points? Well, to find the midpoint, we would use our midpoint formula. M for midpoint. The x coordinate of which is going to be the average of the x coordinates of the 2 endpoints, and the y coordinate of which is going to be the average of the y coordinates of the endpoints. So our x coordinate is going to be -1 plus 3 over 2. Our y coordinate is going to be -3 plus a -7 over 2. Hence, our midpoint is going to be the point 2 over 2 for the x coordinate, and the y coordinates -10 over 2. Hence, we get 1, -5 as being the midpoint, the point that is halfway in between these 2 points in the plane. That is the midpoint. So, ladies and gentlemen, do you think that if I give you 2 unique points in the XY plane, you're going to be able to compute the distance and the midpoint of those points? Do you think you'll be able to do that?
Yes.
All right, basically it's plug and chug. Okay, obviously, you have to know the formulas. And for that reason, you want to, just kind of have these handy in your mind, the distance formula and the midpoint formula. Okay. All right. All right, so that's one thing that I want you to gather out of section 2.1. Another thing, ladies and gentlemen, is we're going to start, we're going to look at equations, okay? And these equations in X and Y do have graphs in the XY plane, various graphs, all right? Okay. I'm going to pose a question here. Is this ordered pair -2, -3 a solution of this equation, x squared plus y equals 1? Do you think that ordered pair is a solution to that equation in X and Y? Well, in order to be a solution to this equation, this ordered pair has to satisfy this equation. To satisfy this equation means that if I replace the x variable with -2, since that's my x coordinate, and I place the y variable with -3, since that's my y coordinate, the left side of this equation has got to be equal to the right side. Is that true or false? This is 4. This is plus a -3. Is 4 plus a -3 equal to 1? Is that true? And that certainly looks like it is what? It is true. So, ladies and gentlemen, is this ordered pair a solution to this equation in X and Y? The answer is
Yes.
yes, it is, because it satisfies that equation. Furthermore, if you were to take the time and graph this equation in the XY plane, then we would expect -2, -3 to be one among an infinite number of points that lie on the graph of this equation in the XY plane, because it is a solution to that equation. All right, let's try another one. Is -2, -3 a solution to this equation? The absolute value of x minus 3 minus y equals 4. Is that true? Is -2, -3 a solution of this equation? Well, if it is, then this ordered pair should satisfy this equation. Well, let's find out. Replace the x variable with the x coordinate. Replace the y variable with the y coordinate. And then verify. Does the left side equal the right side? Well, -2 minus 3 is -5. So we have the absolute value of -5. Subtract a -3. Subtracting a -3 is like adding 3. Is this true? The absolute value of -5 is 5, and 5 plus 3, does that equal 4?
No.
That's false. So the answer is no. This ordered pair is not a solution of this equation in X and Y. And because of that, if we were to graph this equation in the X and Y plane, we would not expect the graph to contain this point. The graph of this equation would not have this point sitting on it, okay? Any questions so far? How we're verifying whether an ordered pair is a solution to an equation in X and Y. Okay. All right, so now the next thing, ladies and gentlemen, is we're actually going to graph some equations in the XY plane. And your author wants you to, first of all, just use the table method. So let's just graph a couple of equations here. Now, why don't we just start with a simple one from elementary algebra? If I wanted you to graph y equals 2x plus 3, do you remember how to graph this equation using the table method? The table method has us doing what? Making a little table here. And we'll call the first column the x column. And then we'll call this second column our equation column. And you can also have a third column if you desire to do so, in which case you can call it your ordered pair XY column. Now, when you're trying to graph an equation in X and Y in the XY plane, you can choose any number you can possibly fathom for X. Doesn't matter what you choose. Whatever you choose for X, though, Y's value will depend upon it according to the definition of this relationship that exists between X and Y. Okay. So, ladies and gentlemen, since you can choose any values for X, why not keep the values simple? In other words, don't choose like 1,000 for X. You're not going to be able to plot that point in the XY plane. So try to keep the choices for X close to 0. Okay, can you give me some nice values for X? Any nice values for X?
1.
1. How about 0? 0 is probably the nicest value you can choose. How about -1? Maybe 2 or -2. Okay, those are good choices for X. All right, to find Y, we're going to have to take, for this first one, with the X value is 1, to find the Y value, we must substitute 1 in place of X and then crank out what Y would be. So if X is 1, Y is going to be 2 times 1 plus 3, or Y is going to be what? 5. Hence, we would have what ordered pair solution to this equation? 1, 5? 1, 5 is one ordered pair solution to that equation. Let's find another one. If X is 0, let's suppose we choose X to be 0. Y, therefore, would have to be 2 times 0 plus 3, which means Y is 3. Hence, 0, 3 would be another ordered pair solution to that equation. Isn't that true? If X is -1, Y would be 2 times -1 plus 3, which gives us 1. Hence, -1, 1 is another ordered pair solution of this equation. If X is 2, Y would be 2 times 2 plus 3, or Y would be 7. Hence, 2, 7 would be another ordered pair solution to that equation. If X is -2, Y will be 2 times -2 plus 3, or will be -1. Hence, -2, -1 is another ordered pair solution to that equation. All right, ladies and gentlemen, why don't we take these ordered pairs now and plot them in the XY plane as we strive to graph this equation. So take some graphing paper out. I will attach some graphing paper to Canvas for your use if you want to download it and print it out, or you can just get your own graphing paper. It's cheap. You can pretty much find it anywhere. Here's your y-axis, x-axis. We will assume these tick marks are 1 unit apart on both the x and the y-axis. 1 unit apart. Okay, we will assume that. So plotting 1, 5 to plot points, we always start at the origin, which is 0, 0, and we move accordingly. 1, 5, its x coordinate is 1. We move 1 to the right on the x-axis, and the y coordinate is +5. Then we have to move up 5 parallel to the y-axis. So over 1 to the right from the origin, now up 5. 1, 2. 1, 2, 3, 4, 5. There is the point 1, 5. In what quadrant does this point lie in? First, second, third, or fourth? What quadrant is this?
First.
That's the first quadrant, okay? Let's plot the point 0, 3. We start at the origin. Notice my x coordinate of 0, 3 is 0. which means we don't move to the right or left on the x-axis. The y coordinate's 3, so we just move up +3, staying on the x-axis, staying at the origin rather. So we move up 3. 1, 2, 3. There's the point 0, 3. Now you can label these points if you want to. It will clutter your graph up, but feel free to do so if you want. Let's plot the point -1, 1. To plot this point, we start at the origin. My x coordinate is -1, so I move 1 unit to the left on the x-axis. Then my y coordinate is +1. Then I move up +1 parallel to my y-axis. There's the point -1, 1. In what quadrant is this point -1, 1 in? What quadrant is this in? What quadrant is this, ladies and gentlemen? This is the first quadrant. This is the
Fourth.
No, this is the second quadrant. This is the third quadrant. And this is the fourth quadrant. Right? First quadrant, second quadrant, third quadrant, fourth quadrant. This point -1, 1 lies in the second quadrant right here. Plotting the point 2, 7. We start at the origin. And how do I move? How do I move to plot 2, 7? From the origin, which way do I go?
To the right.
2 to the right. 1, 2. And then I do what?
Up 7.
Up 7. +1. +2, 3, 4, 5, 6, 7. There's 2, 7. And that point also is in the first quadrant right here. Finally, plotting -2, -1. Start at the origin. And how do I move? -2, -1. How do I move from the origin? -2, -1. X coordinates -2, so we go 2 to the left on the x-axis, and then the y coordinates -1, so we go down 1 unit parallel to the y-axis. There's the point -2, -1, and this point lies in the third quadrant, quadrant number 3. Ladies and gentlemen, it looks like these points all lie on a what? Looks like these points all lie on what? Lie on a straight what? All these points appear to lie on a straight
Line.
line. Should we be surprised that they're on a line? Take a ruler out, put a line through these points and put arrows at the end of that line. Ladies and gentlemen, you are looking at the graph of this equation, y equals 2x plus 3. Any point that sits on this line would be a solution to this equation. You can obviously see that this equation has an infinite number of solutions because there's an infinite number of points that lie on this line. These arrows indicate that the line goes on in respective directions forever. Okay. Ladies and gentlemen, since the graph of this equation is a straight line, this is called a linear equation in x and y. Both y and x are raised to the first degree. This type of relation is called a linear relationship or a linear equation between x and y. And in the word linear, you see the word what? What word is embedded in the word linear?
Line.
The word line. Everybody see that there? So the graph of a linear equation is always going to be a line in the xy plane. Furthermore, this is a rising line. So we would suspect that the slope of this linear equation is positive or negative. What would be your guess?
Positive.
Positive slope. In fact, the slope of that line is going to be +2/1. The y-intercept of this line is the point of intersection between the graph and the y-axis. It happens to be 3. This line intersects the y-axis at 0, 3 right here. That's the y-intercept, we say. Y-intercept. Okay. Is this bringing back memories, ladies and gentlemen?
Yes, it is.
This equation is in a very special form, this linear equation. It happens to be in y equals mx plus b form. Does that ring a bell? Y equals mx plus b form. What form is that called? Anybody?
Slope intercept.
Slope intercept form. The slope of the line is 2 or 2/1, which gives you the measure of rise versus run, which gives you the measure of how steep this line is. You move from one point to another point. You go up 2/1, up 2/1, up 2/1, up 2/1, up 2/1, up 2/1. The y-intercept is 3. That's the point of intersection between the graph of the line and the y-axis. That's your y-intercept, okay? That's why we call this slope y-intercept form or slope intercept form. All right, so that's the graph of that linear equation. All righty. Now, ladies and gentlemen, could we have graphed that linear equation on our graphing calculator? The answer is absolutely yes. Let me show you quickly how to graph this equation on the calculator. All right, this is your graphing calculator. I want you to hit your Y equals button. In the upper left corner of your keyboard is Y equals. Clear any garbage out. For y sub 1, I want you to type in this equation. Y equals 2x plus 3. 2, here's your X button right here above your apps key. X. Hit that button. 2x plus 3. Enter. We have entered that equation into memory. And now, ladies and gentlemen, one other thing is let's just check our window setting to see how our X and Y axis are configured. Hit your window button. Notice my X axis runs from a minimum value of -10 to a maximum value of +10, and the spacing between my tick marks on my X axis are 1 unit apart. My Y axis runs from a minimum value of -10 to a maximum value of +20. I'm going to change that maximum value from 20 to 10. And notice my tick marks are spaced 1 unit apart on my Y axis. Does your window setting look like this? We got this window setting here. Hit the graph button and you'll see the graph of that line. And there it is. Everybody see that there? So that is the graph of y equals 2x plus 3. We showed you how to graph it manually, and we showed you how to graph it using the calculator. All right. Okay. All right, let's try another one here. So we graph that linear equation using the table method. Let's see if next we can graph this simple absolute value function. Y is equal to the absolute value of x. To do that, we will again make a little table and start choosing some values for x, compute what y is, and then we'll plot the points and draw the graph. All right, ladies and gentlemen, give me some nice values for x. Try to keep them close to 0. Don't give me 1 million for x. We're not going to be able to plot that point.
0.
0. Give me some other nice values for x.
1 and -1.
Right, 1, -1. Any others? The more points you plot, the more accurate your graph.
2 and -2.
2, -2. And obviously you could go to the end of time. Do you agree? So that's why these equations have infinite number of solutions, because you have an infinite number of real number choices for x. You can choose decimals and fractions if you want to do. But why do that when you can choose nice values? If x is 0, y must be the absolute value of 0. What's the absolute value of 0? 0. So therefore, the graph of this absolute value equation must contain the point 0, 0. To find another ordered pair solution, let x be 1. So therefore, if x is 1, y is the absolute value of 1. The absolute value of 1 is 1. Hence, we have 1, 1 as being another ordered pair solution. If x is -1, y would be the absolute value of -1. The absolute value of -1 is 1. Hence, -1, 1 is also another ordered pair solution to that equation. If x is 2, y is the absolute value of 2, which is 2. Hence, 2, 2 is another ordered pair solution of that equation. And finally, if x is -2, y is the absolute value of -2, which is 2. Hence, -2, 2 is also a solution to that equation. So we would all suspect these points to lie on the graph of this absolute value equation. So let's go ahead and graph those points and convince ourselves later on what the graph looks like. Okay? So we take a graphing paper here. Always label your axes, very important. Again, we will assume the tick marks are spaced 1 unit apart on both axes. Plotting 0, 0, 0, 0 is just the origin of the XY plane. 0, 0 is right there. Plotting 1, 1, we start at the origin. We move 1 to the right and then up 1. There's 1, 1. Negative 1, 1, we start at the origin. We move negative 1 to the, we move 1 to the left on the x-axis and then up 1. Plotting 2, 2, we start at the origin, we move 2 to the right on the x-axis and then up 2. Negative 2, 2, start at the origin, move 2 to the left on the x-axis and then up 2. Ladies and gentlemen, can you kind of see what kind of graph this is going to be? The graph of this absolute value equation. Connecting these points with straight lines, it appears that the graph of this absolute value equation is going to be a V-shaped graph. Everybody see that there? So that would be the graph of y equal to the absolute value of x. It's a V-shaped graph opening upwards. Any questions how we got that? The graph that on our calculator. Go to y equals your equation editing mode, clear out any garbage. And now we need to type in the absolute value of x. Where do we get your absolute value function? If you hit your math button, go over to number, and it's the first function, ABS. That's your absolute value function. Hit enter. And now we want to type in x, the absolute value of x. My window is still configured from -10 to 10 by 1 on both axes. Hit graph. And ladies and gentlemen, you see the graph of that absolute value equation. Is this making sense here so far? Graphing manually and graphing using the calculator. Any questions so far? Okay. Let's try another one here. Try to graph y equals 1 over x. All right, ladies and gentlemen, how do we graph y equals 1 over x? Well, again, you can use your table method. Make a little table here. Now, can somebody give me some nice values to for x here? Some nice values here.
0,
All right, 0. Any others?
1, -1, 2, and -2.
Maybe something like that. Okay. Now we can certainly try these. I'm going to also maybe choose just a couple more here. 3 and -3 here. All right, so we're going to try this out here. Now, when you put 0 in for x, if x is 0, y is going to be 1 divided by 0. And ladies and gentlemen, 1 divided by 0 is undefined. 1 divided by 0 is undefined. So there is not going to be any ordered pair solution to this equation that has 0 for its x coordinate. It's not going to happen because 1 divided by 0 is undefined. How about 1? If x is 1, y is 1 over 1, or y is 1. 1, 1 lies on the graph. If x is -1, y is 1 over -1. Hence, -1 is the y coordinate. 1, -1 lies on the graph. If x is 2, y is equal to 1 over 2, or 1/2. Hence, 2 1/2 lies on the graph. If x is -2, y is equal to 1 over -2. Hence, -2, -1/2 lies on the graph of that equation. If x is 3, y is 1 over 3, or 1/3. Hence, 3 1/3 is a point that lies on the graph of that equation. If x is -3, y is equal to 1 over -3. Hence, -3 comma -1/3 is a point that lies on the graph. All right, let's see if we can plot these points and get a feel for what the graph looks like. Okay, plotting 1, 1, we start at the origin, move 1 to the right and then up 1. 1, -1 is plotted by starting at the origin, moving 1 to the right and then down 1. Wait a minute here. I don't have this right here. I put -1 in here, correct? That should be -1, -1. Careful, just double check these here. Yeah, it should be -1, -1, so not 1, -1. So plotting -1, -1, start at the origin, move 1 to the left and then down 1 unit. Plotting 2, 1/2, start at the origin, move 2 to the right on the x-axis and only up a half parallel to the y-axis. -2, -1/2, start at the origin, go 2 to the left on the x-axis and then down -1/2 parallel to the y-axis. Plotting 3, 1/3, start at the origin, go 3 to the right and only up 1/3, just a smidget above the x-axis. -3, -1/3, start at the origin, go 3 to the left and then down only -1/3, just a smidget below the x-axis. Okay. So what's happening to this graph? Well, Liz, I'm going to choose like if x is 1/2. And if x is equal to -1/2, what's y going to be equal to? If x is 1/2, y is going to be 1 divided by 1/2, and 1 divided by 1/2 is 2. Hence, 1/2, 2 would be a point that lies on our graph. If x is -1/2, y is going to be 1 over -1/2, which is going to be -2. Hence, -1/2, -2 is a point that lies on the graph. So 1/2, 2, start at the origin, we move a half to the right, but then we move up 2. -1/2, -2, we start at the origin, we move just 1/2 to the left on the x-axis and we move down 2. I got a question for you, ladies and gentlemen. Is this graph ever going to touch the y-axis? Is it ever going to touch the y-axis?
No.
Never. It can't touch the y-axis, because if this graph crosses or touches the y-axis, that means there would have to be a point on the graph that has an x-coordinate of 0. We've already said this function is not defined when x is 0. This graph will never touch the y-axis. Will this graph ever touch the x-axis? Well, ladies and gentlemen, if I let x become very large, like 100, if x is 100, y is going to be 1 over 100. We would have 100, 100th as the ordered pair solution. Do you agree? If I went way out here to the right on the x-axis to 100, my y-coordinate would have me just coming up just a little bit above the x-axis, but not by much. My point is this, ladies and gentlemen. If x keeps getting larger and larger and larger, what happens to the y-coordinate as x gets larger? The y-coordinate is getting what? Smaller. Agree? In fact, ladies and gentlemen, as x approaches very, very large numbers, the y-coordinate is approaching 0. Approaching 0. I didn't say y is equal to 0. In fact, it don't matter how large of a number you put in for x, y will never, ever, ever be equal to 0. It'll be close to 0, but never, ever equal to 0. So this graph is never going to touch the x-axis, no matter how far to the right we choose values on the x-axis. In a similar fashion, ladies and gentlemen, it doesn't matter how small of values you choose on the x-axis, y will never be equal to 0. It will approach 0, but never actually be equal to 0. So the graph of this thing here, therefore, has to look like this. Like that. And then we got another branch of our graph that looks like this. Okay. Goes like that. So this is what the graph of that equation would look like. Y equals 1 over x. Notice the graph gets very close to the y-axis, but will never touch or cross the y-axis. And the graph gets very close to the x-axis, but will never touch or cross the x-axis. For that reason, we say that the x-axis, ladies and gentlemen, is a horizontal asymptote for this graph. It's a horizontal asymptote. The graph will never cross or touch the y-axis, and because of that, we say the y-axis is a vertical asymptote to this graph. A vertical asymptote. Okay? Or we say the graph is asymptotic with respect to the x-axis and the y-axis. Hence, would there be any y-intercepts, ladies and gentlemen? Any y-intercept for this equation? Y-intercept. Is there going to be any y-intercept? Well, I just got done saying the graph will never cross or touch the y-axis. There's no y-intercept. There's no x-intercept because the graph is never going to cross or touch the x-axis anywhere. There's no x or y-intercepts here. Okay, so that one's done. How would we graph that using our graphing calculator? Well, very simple. We have to go to our equation editor, clear out any garbage, and type in 1 divided by x. We will now graph y equals 1 over x. And here's the graph. You can see that's the graph. All right. You see how the graph approaches the x and y axis, but will never ever touch it or cross it. All right. Any questions how we're graphing so far? Okay, so let's try one more. Let's see if we can graph x is equal to the absolute value of y minus 3. Notice things are turned around a little bit now, ladies and gentlemen. This equation is not solved for y, it's solved for x. So in this case, we're going to choose values for y and compute what x is. So we turn the tables a little bit here. Give me some nice values for y. How about -2, -1, 0, 1, 2? Okay. If y is -2, x is going to be the absolute value of -2 minus 3, which is to say 2 minus 3. Absolute value of -2 is 2. 2 minus 3 is -1. Hence, -1, -2 would be a point that lies on our graph. If y is -1, x is going to be the absolute value of -1 minus 3, which is to say 1 minus 3 or -2. Hence, -2, -1 will be a point on our graph. If y is 0, x is going to be the absolute value of 0 minus 3, which is to say 0 minus 3 or -3. Hence, -3, 0 is a point that lies on our graph. If y is +1, x is going to be equal to the absolute value of 1 minus 3. The absolute value of 1 is 1. 1 minus 3 is 2, -2, excuse me. So we would have -2, 1 that lies on our graph. Finally, if if y is 2, x is going to be the absolute value of 2 minus 3, which is to say 2 minus 3, which is -1. 2, -1 lies on the graph. Wrong. It's not 2 -1. What should it be? Not 2 -1.
1 -2.
Actually -1 what? 2, correct? Wait a minute here. I put 2, yeah, it's -1, 2. So be careful when your equations solve for y in terms of x versus x in terms of y. Be careful how you're coming up with these points here. So -1, right? -1, 2, -1, 2 would lie on the graph. All right, let's take our graphing paper out and graph this and take a look at it. So take our graphing paper out, label the axes. Let's plot some points. -1, -2. Start at the origin, 1 to the left, down 2. That point lies in the third quadrant. -2, -1. Start at the origin, move 2 to the left, and then down 1. That point lies in the third quadrant. Start at the origin to plot -3, 0, and we go 3 to the left, and we stay on the x-axis. Okay, hold on a second, I'm just looking at these points here. All right, then we want to plot -2, 1. So we start at the origin, we go 2 to the left. Wait a minute here. -2, 1. Double check these points. Just make sure we got these coordinates right here. Okay. This should be, when you put 1 in there, you get -2, 1. Okay, got that. Put 2 in there, you get 2, -1, 2. All right, so let's see, -3, 0 is there. And now, Liz Ellen, we're going to try to plot these other points here. So we got what? -2, -2, 1. -2, 2 to the left, and then up 1. And then we got -1, 2. Start at the origin, 1 to the left, up 2. All right. There you go. Okay, and if you plotted more points, you would see that your graph is, it's going to be a V-shaped graph. And this graph here is going to open to the right, okay? So that graph's going to open to the right. So, Les, it looks like this graph opens to the right. Everybody see that there? A V-shaped graph. All right. Okay, now to graph this on the calculator, unfortunately, we can't do that because our calculator only allows us to graph equations that are solved for y. So, I mean, we would have to solve this equation for y, and that could be done. But you'd have to solve this equation for y first, in which case you'd have to isolate the absolute value by adding 3 to both sides of this thing. And then you would get rid of your absolute value symbols and saying that y is either equal to positive x plus 3 or y is equal to what? Negative x plus 3. So we get 2 equations to graph in our calculator, y equals x plus 3 or y equals negative x minus 3. Then you could graph both these equations and you would have the graph of x equals the absolute value of y minus 3. So let's see if we can graph both those equations on the calculator. Okay, hold on a second here. Clear out any garbage. And then you'd have to type in y equals x plus 3. And the other equation is going to be y equal to negative x minus 3. Hit graph. Okay. And when you hit graph, ladies and gentlemen, you are going to see the graph of 2 lines here. All right. The problem is we should not be seeing these lines to the left of what? To the left of -3 here on the x-axis. All right. So all we see is this V-shaped graph opening to the right here when we graph ours. We don't see it to the left there. So you can see that there are some complications when you try to graph a linear equation, or excuse me, any equation that's solved for x in terms of y. Your calculator is kind of geared for solving equations that are solved for x, okay, where y is in terms of x instead of y. But nonetheless, we can see that we can solve or graph these really by using our table method, nonetheless. Okay. All right. Okay, so what are X and Y intercepts? Do you remember what X and Y intercepts are? I've been kind of throwing those around loosely here. So suppose that I had the graph of maybe a linear equation here, and the graph of it looks like this. Well, I'm the point of intersection between the graph and the y-axis is called a y-intercept. So that would be the y-intercept of this graph here. The point of intersection between the graph and the x-axis is called the x-intercept. Now, notice a y-intercept lies on the y-axis, and therefore, in order to find the y-intercept, since a y-intercept point is on the x-axis, we would always set x equal to what? 0. Y-intercepts always have an x-coordinate of 0. To find the x-intercept, since an x-intercept is a point of intersection between the graph and the x-axis, and the point lies on the x-axis, its y-coordinate would always have to be what? 0. All right, so in order to find a y-intercept, you set x equal to 0. To find x-intercepts, you set y equal to 0. All right, I'm going to go in our book here to page 174. In our textbook. Got to log in. It timed me out. Hold on a second. All right, so I want to go to page 174 in our textbook. All right. Okay, problem number is 46. I'm going to give us the graph of some sort of relationship involving x and y, and they want us to estimate the x and y intercepts. So what would be the x-intercepts of this circular graph in blue here? Anybody? The x-intercepts.
Negatives.
Go ahead. What do you? The x-intercepts are the point of intersection between the graph and the x-axis. So we do see what we want over here at -16 and also at +4. So as ordered pairs, your x-intercepts would be -16, 0, and 4, 0. And your y-intercept would be what? Your y-intercepts would be +8 and -8. There you go. So 0, 8 and 0, -8 would be your two y-intercepts. That makes sense? Okay. All right. So from a graph, it's pretty easy to determine what the x and y intercepts are. For number 49 here, the graph of this parabola opening to the right, what would be the y-intercept?
0.
The origin, 0, 0. What would be the x-intercept?
0.
Also 0, 0. All right. What would be the x-intercepts of this ellipse here, number 50, this ellipse?
0 and 6.
0 and 6, so 0, 0 and 6, 0, do you agree, would be the two x-intercepts? What would be the y-intercept?
0, 0.
The origin, 0, 0. Okay, 0, 0. All right. Now, how do we find these things algebraically if we don't have the graph? Well, suppose that I have this linear equation, -3x minus 5y equals 60. And ladies and gentlemen, I want to find the x and y intercepts. How do I find the x-intercept? What do I set equal to 0? find an x-intercept, we always set y equal to 0. So therefore, y becomes 0. Take 0, substitute it into your equation for the y variable. This term now drops out, and now we have to solve for x. To solve for x, we divide both sides by -3. X is equal to -20. So your x-intercept would be the ordered pair -20, 0. That's your x-intercept. It's at this point where this line is going to intersect the x-axis, right there. To find the y-intercept of this linear equation, we set what equal to 0? X gets set equal to 0 always. So now we let x be equal to 0. Take 0, substitute it in for the x variable into the equation. This term drops out. We're left with -5y equals 60. Solving for y, dividing both sides by -5. We get y is equal to what? What's 60 divided by -5? That would be a -12. Hence the ordered pair is 0, -12. That's your y-intercept. It's at this point where the graph of this linear equation is going to intersect the y-axis. Okay. Any questions how we manually found the x and y intercepts of that linear equation there? Let's see if we can find them using our graphing calculator. Well, in order to graph this equation, first of all, we got to solve this equation for y. How do I solve this equation for y, ladies and gentlemen, so I can present it to the machine? How do we solve for y?
Add 3x to both sides.
So first, we're going to add 3x to both sides. The 3x's drop out on the left side, leaving you with -5y. And on the right side, I'm going to spin these around. We'll have 3x plus 60. Dividing both sides by -5 now, we will therefore have accomplished our task of solving for y. Now, you know, I mean, you could leave it like this, or you could split it up into -3 over -5 times x plus 60 over -5. Legal to split this up. In fact, if you want your equation to be in slope-intercept form, you would have to do this anyways. So the slope of this line is -3/5, and the y-intercept is 60 divided by -5, which is -12. That's your y-intercept. Hey, ladies and gentlemen, look at your y-intercept as -12. Did we not get 0, -12 for the y-intercept? Y-intercept is -12 from slope-intercept form. We got -12 for the y-intercept. Things are looking good. All right, so let's take this to our calculator and graph it. Let's type that into our graphing calculator. So, all right, so I'm going to type in -3/5. So open parenthesis, -3 divided by 5. That's how I enter a -3/5 times x minus 12, subtract 12. I have entered that equation into memory. Now we can graph this line. Ladies and gentlemen, I'm going to have to, since my x-intercept is going to be -20, 0, I'm going to have to tweak my window a little bit here. So on the x-axis, I'm going to have to go further to the left to -10. I'm going to have to go out to maybe -25. I'm going to take it out to -30 on the x-axis. So I'm going to go from -30 to 10 on the x-axis, and my y-axis will run from -15 to maybe +15. Okay. That's how I'm going to configure my x and y axis. Now, when you hit graph, you will see the graph of that line there. Everybody see it? That is the graph of y equals -3/5 x minus 12. Notice the slope of our line is -3/5. And because the slope's a negative slope, this is a falling line. We would expect this line to be a falling line, and it is a falling line. Okay, falling lines have negative slopes. All right, how can we have our calculator find the x and y intercepts? First, let's show you how to find the x-intercept using your graphing calculator. With your equation graphed, you need to go into your calculate mode. So you would hit your second button followed by the trace button to get into calculate. Second, trace takes you into calculate. Another name, ladies and gentlemen, for an x-intercept is a zero of a function. All right, because it's a value that sends your function's y value to a value of 0. That's why it's called an x-intercept. I want you to go down and select the 0 function on your calculator. Hit enter. Now your calculator is going to want us to establish a left and right bound that boxes in our x-intercept. So with my blinking cursor here, I want to move my blinking cursor using my arrow keypad so that it's to the left and a little bit above the x-intercept I want to find. Just move your blinking cursor somewhere in here. Notice this blinking cursor projects vertically down to the x-axis at a point that's to the left of my x-intercept. That's why we call this a left bound. Hit enter. Now your calculator wants a right bound. So now we have to navigate our blinking cursor below and a little bit to the right of the x-intercept we wish to find. If I put my blinking cursor here, notice my blinking cursor projects vertically up to the x-axis to the right of the x-axis I wish to x-intercept I wish to find. For that reason, we call that a right bound. Hit enter again, and boom, your calculator zeroes in and finds that x-intercept, which is -20, 0. That's your x-intercept.
I can't get mine to show the area like that. It just shows the 4 quadrants, and I can't get it to move.
Are you seeing the graph?
Yeah, I do. I see the graph here. I'll
Get your window button. Hold on a second. I gotta enable you. Okay. I'm sorry. Hold on a second here. What? Wait a minute. Hold on.
So I'm
Okay.
just seeing the original graph. I think I might have missed a step.
All right. Well, let's go back here and just check a couple things here. So first of all, hit your window button. Is your X and Y axis configured accordingly as mine?
Nope, that's where it's from. I must have missed
Because
it.
if you don't have your X and Y axis configured accordingly, ladies and gentlemen, you may not even see your graph. Sometimes you have to tinker with your X and Y axis configuration to see your graph. Okay.
Okay. Now it looks like.
So
yours.
now when you hit the graph button, you should see the graph. And how do we find the x-intercept again? We went into calculate, second trace, calculate, and we went down and used the 0 function. The 0 function always finds x-intercepts. So hit enter to activate the 0 function. Your calculator wants you to establish a left bound. So you got to move your cursor so it's a little bit to the left of the x-intercept we want to find. Somewhere in there, we'll call that a left bound, hit enter. Now your calculator wants us to establish a right bound. So now you got to navigate this little blinking cursor so that's a little bit to the right of that x-intercept, somewhere down in here. Hit enter. Now,
Okay.
when your calculator says guess, just hit enter again, and your calculator should find that x-intercept.
Got it.
Did it work? Okay.
Yes. Yep.
All right. So notice that's how you graphically find x-intercepts, ladies. I'm using your 0 function and calculate. Now to find the y-intercept, we're going to go back to calculate, second trace, but this time we use the value function. The value function finds y-intercepts. The 0 function finds x-intercepts. To find the y-intercept, we activate the value function in calculate. Here we go. Ladies and gentlemen, what am I going to type in for x if I want to find the y-intercept? Y-intercepts must always have what for an x coordinate?
0.
0. We type in 0, hit enter, and there's your y-intercept, 0, -12, with the blinking cursor sitting on that point. Questions? Do we understand how to find x and y-intercepts using our calculator, ladies and gentlemen?
Yes. Thank
Value
you.
function finds y-intercepts, 0 function finds x-intercepts, okay? All right. So we got that now. Let's see here. Okay. Well. Okay, let's see if try another one here. Suppose I want to find the x and y intercepts of this equation, y equal to the absolute value of x plus 4 minus 3. How would we find the x and y intercepts? How do we find an x-intercept? We set what equal to 0 to find an x-intercept. We always set y equal to 0. Take 0, substitute it in for the y variable in this equation, and now we're going to have to solve this absolute value equation. To solve this absolute value equation, we're going to have to, first of all, isolate the absolute value by adding 3 to both sides. Then, ladies and gentlemen, recall from in the past, to solve an absolute value equation now, we drop the absolute value symbols and we set x plus 4 equal to positive 3, and we set x plus 4 equal to what? Negative 3. Then we have 2 equations to solve. Subtracting 4 from both sides here, we get one x-intercept as being -1. Subtracting 4 from both sides of this equation, we get another x-intercept, which is -7. So you got 2 x-intercepts, -1, 0, and also -7, 0. Those are your 2 x-intercepts of the graph of this absolute value equation. To find the y-intercept, what do I set equal to 0?
X.
X. Take 0, substitute it in for the x variable into the equation, and then solve for y. So y better be equal to the absolute value of 0 plus 4, subtract 3. Y better be equal to the absolute value of 4, which is 4 plus 3. Y would be equal to 7. Hence, our y-intercept is 0, 7. That's your y-intercept. Hence, the graph of this absolute value equation has 2 x-intercepts and it has 1 y-intercept. Let's see if we can graph this equation in our calculator, ladies and gentlemen, and convince ourselves that these are the intercepts. So let's throw this equation into our graphing calculator now. Let's go to our graphing calculator.
In the y-intercept, it has the 4 minus 3, but that turned into 4 plus 3.
No, because what's the absolute, wait a minute, what do I got there? Son of a gun. It is 4 minus 3. My apologies, ladies and gentlemen. I don't know what is going on. I don't know why I'm starting to miss little things like that. Maybe that's a sign of old age or something. Wow, that's scary. 4 minus 3 is 1, correct? So
Yes.
our y-intercept should be 0, 1. Thank you for that. Unreal. I hope this is not a precursor of things to come in my life. That is bad news. All right, let's take this to the calculator and try to graph it and convince ourselves those are the intercepts. So we go to y equals, clear out any garbage. Now, ladies and gentlemen, we're going to type in the absolute value of x plus 4. Do you remember where we get the absolute value function from? We hit our math button and go over to the number mode, and it's the ABS function. Math, number, ABS, absolute value. Type in x plus 4, x plus 4. Hit your right arrow key to get out from inside the absolute value function. Now type in -3, right? -3. Ladies and gentlemen, we're about to graph this function here. Oops, I shouldn't have said function. That's something to come in the next section. We're going to graph this equation. Hit graph, and we see the graph here. Do we see the graph? Is it a V-shaped graph opening upwards?
Yes.
All right, to find our x-intercepts, we got to go to calculate, second trace, calculate mode. Go down and grab our 0 function. Let's activate the 0 function. Now, if you want to find this x-intercept over here to the left, you're going to have your cursor in the vicinity of this one over to the left. If you want to find the x-intercept over here to the right, you're going to have your cursor in this vicinity over here to the right. Okay, I want to find the x-intercept to the left over here. So my left bound looks like my cursor is in a good position to establish a left bound for this leftmost x-intercept. So hit enter. Right bound, just navigate the blinking cursor so it's a little below the x-axis. So that's a little bit to the right of that x-intercept, somewhere in here. Hit enter. Hit enter again, and you'll see that there's one of your x-intercepts, -7, 0. That was one that we got algebraically. Now, ladies and gentlemen, I want to find this x-intercept to the right over here. So we got to go back to calculate. 0 function. But this time we got to navigate our cursor in the vicinity of this other x-intercept. Notice, by virtue of the way the graph goes to the x-axis here, a left bound is going to have my cursor below the x-axis here. Do you agree? That's a left bound for this x-intercept to the right. Hit enter. Now a right bound is going to have us bringing that cursor a little bit above the x-axis so that it's to the right of that x-intercept. Hit enter. Hit enter again, and your other x-intercept is -1, 0. That's the other one we found algebraically. Finally, to find the y-intercept, we go to calculate and use what function?
Value.
The value function, and we type in 0 to find the y-intercept always. So type in 0 for x equals 0, hit enter, and ladies and gentlemen, you get your y-intercept, which is 0, 1. 0, 1. Do we understand how to find x and y intercepts on a graph now using the graphing calculator? Do we understand, ladies and gentlemen, how to find x and y intercepts algebraically, manually? Okay. All right. So we will be expected to do, utilize both techniques for finding these intercepts here. All right. Okay, so I am going to close the door on that section, ladies and gentlemen. I think we've seen everything we need to see out of section 2.2 there. 2.1, excuse me. That was 2.1, my bad. We're not doing 2.2. We're going to jump now to 2.3. 2.3, ladies and gentlemen, is entitled Functions and Relations. First of all, I'm going to define for you, this is a definition. This is short for the word definition. I'm going to define for you what a relation is. Ladies and gentlemen, a relation in mathematics is a set of ordered pairs. A relation is a set of ordered pairs. Okay. This, ladies and gentlemen, is an example of a relation. If I have a set consisting of these ordered pairs here. Notice there's a finite number of ordered pairs here that we could plot in the XY plane. Nonetheless, we do have a set of ordered pairs. So by definition, this is called a what? This is a relation. This is called a relation. It's a set of ordered pairs. It's a relation. Ladies and gentlemen, when we work with relations and also functions, of which I will define in a second, oftentimes we're concerned with two very important sets. The first set is called a domain. What's a domain of a relation or a function? Hint of things to come. The domain, ladies and gentlemen, is basically the set. It's a set of all x coordinates. It's a set of all x coordinates. What's a range of a relation or a function in mathematics? It's a set. It's a set of all y coordinates. So what would be the domain, ladies and gentlemen, represented by uppercase D here? What's the domain of this relation up here? What's the domain? What's in my domain for this relation? That would be all the what? X coordinates. Which?
3, -2, 5, and 1.
1, correct? That's the domain. What would be the range denoted as uppercase R? The range of this relation.
-4, 0, 0, 0.
You don't have to list 0 3 times. There you go. So ladies and gentlemen, this is the range. Do you agree? The domain consists of all the x coordinates of the relation. The range consists of all the y coordinates. There you go. Do we understand what a domain and range is so far for a relation? All right. Now, next definition, ladies and gentlemen, I need to define for you what a function is. What is a function in mathematics? Another definition. A function in mathematics is a relation in which no two different ordered pairs have the same x coordinates. In other words, ladies and gentlemen, all the x coordinates have to be unique for a relation to be a function. Here's an example of a function. This set of ordered pairs represents a function. Yes, it's a relation because it's a set of ordered pairs, but this is a special type of relation known as a function. Because notice all the x coordinates are unique. There's no duplicate x coordinates with two different ordered pairs. They're all different x coordinates. That's why this is called a function. This is an example of a relation that is not a function. This would be an example of a relation that is not a function, but only a relation. Why, ladies and gentlemen, is this only a relation and not a function? Why is this not a function?
The 3 repeats.
You got two different ordered pairs with the same x coordinates. For that reason, ladies and gentlemen, this is not a function. It's just a relation. So all functions are relations, but not all relations are functions. Let me say that again. All functions are relations, but not all relations are functions. All right. Ladies and gentlemen, one way to represent a relation or a function is to represent it as a set of ordered pairs. But in all reality, some relations or functions have an infinite number of ordered pairs. How are we going to list an infinite number of ordered pairs? That's impossible. So sometimes another more convenient way of representing a function or a relation is to have the graph of the function or the relation. And I want to go now, ladies and gentlemen, to page 185 in our textbook. Example number 3 in your textbook. Hey, I have a question. How many people actually look at the examples in the sections that I cover in class? Anybody do that outside of class? Look at the examples?
I do when I'm doing the textbook homework if I'm struggling with something.
And that is smart. Ladies and gentlemen, if you want to solidify or if you want to enhance my lectures as far as your understanding is concerned, you might want to also go through and look at some of the examples in the sections I cover. Very valuable. Okay, it's only going to reinforce things in your mind. All right, now, ladies and gentlemen, suppose that we have the graph of a relation in the XY plane. Look at A here for example 3. Notice we have the graph of this blue curved graph. We got a blue curved graph here, okay, which represents a relation. Why is it a relation? Because there's ordered pairs on this blue curve. In fact, how many ordered pairs are on this graph, ladies and gentlemen? How many ordered pairs or points are there? How many ordered pairs or points are there on this graph, this blue curve here?
2. Oh no, 4.
2, 4. Ladies and gentlemen, this is a continuous what? Blue graph here. Do you agree? There's an infinite number of ordered pairs on this thing. There's no breaks in this graph anywhere. There's an infinite number of ordered pair solutions that lie on this graph. Furthermore, this graph goes up forever because the arrow says it does. It goes down forever over here because the arrow says it does. All right. Now, so this is definitely a relation. This graph represents a relation because it's a set of ordered pairs. In fact, it's a set of an infinite number of ordered pairs. Ladies and gentlemen, is this relation a function? Well, when you have the graph of a relation, you can tell if it's a function by subjecting its graph to what's called the vertical line test. The vertical line test. The vertical line test is a very simple way to determine ladies and gentlemen, whether the graph of a relation qualifies as being a function. To administer this test, all you have to do is take a hypothetical vertical line and move it anywhere in the XY plane, from left to right or right to left. If your vertical line touches the graph and at most 1 point, then your relation is a function. Do you agree it doesn't matter where I put a vertical line in the XY plane, it will touch the graph or intersect the graph and at most 1 point? Do we see that?
Yes.
So ladies and gentlemen, we say this graph passes the vertical line test. So this would be an example of a function. Let's look at number in B. Let's look at this one. We have the graph of a relation, which is like a parabola that opens to the right. Ladies and gentlemen, is this relation a function? Does its graph pass or fail the vertical line test?
It fails the vertical line test.
It fails the vertical line test because notice you can put a vertical line like right here, and you can clearly see that that vertical line is intersecting the graph at more than 1 point. What's the big deal with this vertical line test? Well, ladies and gentlemen, do you agree that there's 2 points that sit on this blue curved graph that have the same x coordinates? This point up here and this point down here. Do you agree they have the same x coordinates? And because we have 2 different points with the same x coordinates, this relation is not a function. That synonymously is saying that's why the graph fails the vertical line test. That's just a relation, not a function. How about this piecewise relation where it's broken up into pieces? Ladies and gentlemen, is this relation a function? Does a vertical line placed anywhere in the plane touch the graph and at most 1 point?
Yes.
Looks like no matter where you put a vertical line, it touches the graph and at most 1 point. Oh, wait a minute. What if you put a vertical line through x equals 1? Doesn't it touch the graph in more than 1 point? Yes or no?
Not technically.
Technically, it doesn't, because this is an open circle here, ladies and gentlemen. The point 1, 2 does not lie on the graph of this relation. The point 1, 4 does, because that's a closed circle. So, ladies and gentlemen, this is a function. This relation is a function. This graph passes the vertical line test. Okay. All right. So do we understand the vertical line test and what it can tell us about whether the graph of a relation is a function or not? Does that make sense, ladies and gentlemen?
Yes, it does.
Okay. How about this one here? A, would this relation be a function?
No.
No. You can put a vertical line. Let's say you can put a vertical line through x equals 3, and you agree that vertical line would touch the graph in more than 1 point?
Yeah.
So hence there must be what? There must be at least 2 points with the same x coordinates of 3. Do you agree? That's not a function, that's a relation. How about B? Is this parabola opening upwards a function?
Yes.
The answer is yes. The graph would pass the vertical line test. How about this graph that's broken up into pieces? Is this a function, ladies and gentlemen?
No.
No. Why? Where would you put the vertical line such that you could show that it touches the graph in more than 1 point?
-2.
At x equals -2, notice if you put a vertical line through x equals -2, that vertical line would touch the graph in 2 points, namely -2, 3, and also the point -2, 4. Because of that, there's 2 different points on this graph that have the same x coordinates of -2. This is not a function, it's only a relation. The graph fails the vertical line test. Is this making any sense, ladies and gentlemen, the vertical line test, and what it can tell us? All right. Okay, let's get back to this now. All right, ladies and gentlemen, y equals 7x plus 3. If you were to take the time and graph this linear equation, why is it linear? Because both x and y are to the first power. It's a linear relationship in x and y. This, ladies and gentlemen, is called the definition of this equation because it defines what y's value will be. So this is called the definition. X is called the input variable, or sometimes it's referred to as the independent variable. Y is called the output variable of this relationship. Sometimes y is called the dependent variable. If you were to graph this linear equation, notice it's in what form? It's in slope-intercept form, y equal to mx plus b form. So if you were to take the time and graph this linear equation, which we're not going to do, the y-intercept would be where? What's the y-intercept?
3.
3. So we know the graph would have to go through the y-axis at 3 here. Furthermore, the slope is positive 7 over 1. So since it's a positive slope, this would be a rising line. So if you graphed it, it would look something like this. Ladies and gentlemen, is this relation a function? Does its graph pass the vertical line test?
Yes, it does.
Notice the graph does pass the vertical line test because no matter where you put a vertical line, you can only touch the graph and at most 1 point anywhere. Hence, we are looking at a function. This is a function in mathematics. All right. Okay. Ladies and gentlemen, the thing that characterizes what this function is all about is the almighty definition of this function, because it tells us what happens to an input value. The definition says when you put something into this function, it gets multiplied by 7, and then we add 3 to that value. It's the definition that characterizes what the graph of a function will look like. It doesn't matter, ladies and gentlemen, what you call the input and output variables. For that reason, oftentimes in higher level math, instead of using y for the output variable, they tend to use functional notation. So they tend to use maybe this for the output variable. Instead of y, they like to maybe call it f of x. This is called functional notation. You read it as f of x. That's how you read that notation, f of x. F of x is no different than y, no different whatsoever. Notice the definition of this function is still the same, and because of that, the graph of this function will be identical to the graph of this function. The only difference is, instead of labeling the vertical axis as the y-axis, now you will call it the what axis? What axis are we going to call the vertical axis?
F of x.
The f of x axis. That's the only difference. The graph is still the same. Nothing changes. Nothing changes with the graph because nothing changed with the definition of this function. We're still multiplying the input by 7 and adding 3 to it. Okay. If I give you this, ladies and gentlemen, what is this saying to do? If I say find this, if I say find f of 4, that's how you read what you're looking at, f of 4. What does that mean to do? Does anybody know what this means to do? How do we find f of 4?
Enter 4 as x.
We're putting 4 into our function, f of x. So x becomes 4, which means wherever you see x in the definition of the function, you replace x with 4. So f of 4 is going to be 7 times 4 plus 3, which gives us a value of what, 31? What ordered pair, ladies and gentlemen, have I generated that's a solution to this function or this function, or would have to lie on this graph? What ordered pair did I generate? What ordered pair did I just generate here? What's my x coordinate of my ordered pair? What's my y coordinate?
4 and 31.
4 is the x coordinate. The y coordinate is what? 31. 431 would be a solution to this function or this function, and we would expect it to be a point on this graph. You'd have to go kind of high up on the y-axis, but it would be up here, way up here. 431 would be up here, a point way up here, okay, on the graph. All right, what is this saying? F of -2, do you agree? Help me find f of -2. How do I do that? I replace what with -2? X becomes -2. So f of -2 is 7 times -2 plus 3, which is going to be -14 plus 3, which is -11. Hence, the ordered pair -2, -11 would also be a point that lies on this graph. -2, -11 would be down here somewhere. Do you agree? -2, -11 would be here in the third quadrant here. Isn't that true? Somewhere over there? All right. All right. F of 0, what would f of 0 be? That means we put 0 in for x. Hence, f of 0 or y would be 7 times 0 plus 3, which is to say 0 plus 3, which is 3. You recognize this point, ladies and gentlemen? 0, 3 is the what? It is the what intercept?
Y-intercept.
0, 3 is the y-intercept, y-intercept, y-intercept. You agree?
Yes.
Do you always have to put a number into a function? The answer is absolutely not. You can put anything you want into a function. I could evaluate this function at some variable a, in which case the output would be 7a plus 3. I could put maybe a variable expression into my function like c plus 2, and the output would have to be 7 times c plus 2 plus 3. Which after you simplify this by distributing and gathering together like terms, we would have 7c plus 17, agree? So if you put c plus 2 into this function, you get this out. A function is kind of like a machine. Think of it as being a machine. You put something into the machine operates on that input according to its definition and spits something out. Input, output, input, output, input into the machine, output. Input, output. You see that? All right. Now, ladies and gentlemen, we got to go back to our textbook. What did I say the domain of a function was? Did anybody remember the definition of a domain I gave you about an hour ago?
The set of all x coordinates.
Set of all x coordinates of a relation or a function. The degree is called the domain. All right. And what was the range?
Set of all y coordinates.
Set of all y coordinates. All right. Let's go to page 188. And on page 188, ladies and gentlemen, I want to look at example 8 here. Example 8 on page 188. All right, ladies and gentlemen, they want us to find the domain and range of these relations and or functions. Look at A here. We have the graph of a relation because we have what? A graphing of a finite number of points, ordered pairs. It's a set of ordered pairs. So it's a relation. Is this relation a function? Does this graph pass the vertical line test?
Yes.
Yes, it does. So it's a function. What would be the domain of this function, ladies and gentlemen? What are all the x coordinates that would be in my domain?
-3, -1, 0, 2, and 4.
Yes, -3, -1, because this point has its x coordinate as -1. 0 would be in our domain. This point has 0 for its x coordinate. 2 would be in the domain. 4 would be in the domain. What would be the range? Set of what values?
-4, 1, 3, and 4.
And 4. That's right. -4 would be in the range because this point here has its y coordinate value as being -4. 1 would be in the range because this point 0, 1 has its y coordinate as being 1. 3 would be in the range because the y coordinate of this point is 3. 4 would be in the range because both these points have its y coordinate value as being 4. Good. Ladies and gentlemen, more difficult question now. What would be the domain of this function here? Notice I called it a function, so the graph obviously has to pass the vertical line test, which it does. So, ladies and gentlemen, what would be the domain of this function? Notice now, unlike this one up here where we had a finite number of values in the domain and range, this is going to have an infinite number of values in the domain. And because there's an infinite number of values, we cannot list them all. Because of that, ladies and gentlemen, we're going to have to maybe use interval notation to represent the domain of this function. Anybody want to give it a stab as to what the domain would be for this function? The domain. Remember, the domain is a set of all x coordinates of all points that lie on the graph of a function. What would be the smallest x coordinate on this graph?
0.
Well,
Oh,
the
the smallest would be
smallest x coordinate.
-3.
Yeah, that would be the point furthest to the left. Unfortunately, ladies and gentlemen, there's an open circle on this point, -3, -2. So -3 does not actually belong in the domain. However, do you agree that the domain would consist of all real numbers that are what? Strictly greater than what? -3?
Yes.
You agree any other number on the x-axis that's greater than -3 would be what in the domain, because it would have a point on the graph that has that value for its x coordinate? Doesn't this
Yes.
graph go to the right and up and to the right forever? So ladies and gentlemen, the domain would be from -3, not including -3, up to positive infinity. Let's see if we can get a visual on that. Ladies and gentlemen, do you understand right here that the domain, okay, is the graph of all these real numbers on the x-axis here, not including -3, up to what? Positive infinity. Everybody see that there? It's this green shaded line that goes to the right on the x-axis. That's your domain. That's the graph of your domain for this function. Interval notationally, we would say the domain is what? Open parenthesis, -3 to positive what? Infinity. Agree? That's the domain. All right, what would be the range of this function in B, ladies and gentlemen? The range. The range pertains to all the y coordinates of all the points on the graph. What's the smallest y coordinate found for any point on this graph? The smallest y coordinate. Well, since we have an open circle at -3, -2, -2 is not actually in the range, but we could get infinitesimally close to -2. Agree? Okay. So ladies and gentlemen, the range will consist of what? All real numbers that are strictly what? Greater than -2? Remember, this graph goes up forever. This arrow means this graph goes up forever. So the range is denoted by this brown shaded arrow on the y-axis. So the range is all real numbers that are what? Strictly greater than -2. Hence, the range using interval notation is denoted as open parenthesis -2 to infinity. Is this getting through, ladies and gentlemen? Domain and range.
Yes.
What would be the domain of this parabola opening downwards here, which is a function, its graph passes the vertical line test? What would be the domain of C here?
-infinity to infinity.
Yeah, because look at these branches here are going to keep going down forever. But ladies and gentlemen, as they go down forever, they spread further and further apart from each other. You need to understand that too. And since they've spread further and further apart from each other forever, you agree it doesn't matter what value you choose on the x-axis, you could always project it down far enough or up high enough and hit a point on the graph? You agree with that? Doesn't matter what value you choose on the x-axis, you could always project it down far enough or up far enough and hit a point on the graph. Isn't that true? So the range is all real numbers, ladies and gentlemen, from negative to positive infinity. Notice the green shading that goes both to the left and to the right. Hence, the domain is represented from negative infinity to positive infinity using interval notation. What's the range of this parabola? What would be the smallest value in this range? The smallest y coordinate of any point found on this graph? Well, actually, there is none, because this graph goes down forever. Do you agree? So there is, ladies and gentlemen, no lowest point on this graph, because if you give me a low point, I can do better than that, give you a point lower on the graph than that. Then you could turn around and give me one lower than that. Then I could turn around and give you a point lower than that, et cetera, et cetera. So our range goes from negative infinity up to what's the highest or largest y coordinate found for any point on this graph?
4.
Positive 4. Do you agree? This point here, 2, 4, is the maximum point on this parabolic graph. It has the largest y coordinate of any point on this graph. So the range of that parabola opening downwards, okay, goes from negative infinity all the way up to what? Positive 4, including 4. Hence, interval notationally, we would represent the range as open parenthesis, negative infinity, comma to 4, including 4, hence the bracket. Is this making sense with domains and ranges, ladies and gentlemen, of functions?
Yes.
Yes.
Okay, if not, please do study this example 8 on page 188 and try to do some of these extra, try to do this problem here. There's another practice problem here. Although, yeah, okay. Well, we could look at this one. Why don't we look at this one B here? It's this graph, this V-shaped graph that goes up forever to the left, but not to the right. What would be the domain, ladies and gentlemen, of this function here? Notice it is a function. This graph passes the vertical line test. What's the smallest value found in the domain? What's the smallest x coordinate of any point on this graph? Well, this graph goes to the left forever, does it not? So the smallest value in the domain is negative infinity up to, what's the largest x coordinate found for any point on this graph?
4.
Positive 4. So the domain would be open parenthesis negative infinity up to 4. That's the domain of this function. The range, what's the smallest y coordinate of any point on this graph? What's the smallest y coordinate?
-4.
Negative 4. That's the lowest point on this graph. Hence, the range is from -4 up to what? Positive what? Infinity, because this graph goes up forever. Hence, the range is from -4, including up to positive infinity. There's the range. All right, so ladies and gentlemen, do we know how to find the domain and range from a graph of a function or a relation? Can we find the domain from an equation of a function or relation? The answer is absolutely yes. So ladies and gentlemen, suppose I want you to find the domain of maybe this function here. F of x is equal to x plus 6 over x minus 2. An alternative definition for the domain of a function, ladies and gentlemen, is that it's the set of all real numbers for which the function is defined. Can you tell me if there would be any value that would have to be excluded from the domain of this rational function? Would we have to exclude any value?
2.
2. Do you agree if our denominator becomes 0, ladies and gentlemen, this thing's undefined? So what causes our denominator to become 0? Well, that would be a value of 2. Do you agree? So the domain of this function is all real numbers except what? X cannot be equal to 2. Doesn't that make sense? Or else this function's undefined. If you try to evaluate this function at 2, ladies and gentlemen, this thing is going to be undefined. You're going to have 8 divided by 0, undefined. All right. So what would be the domain of this function? Using set builder notation, we could say it's the set of all real numbers x such that x cannot be equal to what? 2. This is called set builder notation or set notation for representing a set. Using interval notation, how would I represent all real numbers except 2? Well, here's how we would do it. We would have, first of all, how would we graph all real numbers except 2 on the number line? Well, we cannot include 2. So we would have to include all numbers less than 2 and all numbers that are strictly what? Greater than 2, but we cannot include 2. This would be the graph of the domain of this function. How would we, using interval notation, represent this domain? We would say the domain D is from negative infinity up to 2, but not including 2, in union with not including 2 up to positive infinity. This is the interval notational way of saying all real numbers except 2 are in the domain of this rational function. That's the domain. How about this function k of x? What would be its domain? What would be its domain, ladies and gentlemen, for this rational function k of x? Well, we got to make sure the denominator never becomes what? 0? What value or values would send this denominator to 0? Are there any real numbers that would send this to 0, this denominator? Well, let's try to solve this equation and find out. Subtracting 2 from both sides, taking the square root of both sides. We get x is equal to plus or minus I times the square root of 2. Ladies and gentlemen, these are not real. So my question is this: are there any real numbers that cause my denominator to be equal to 0? Are there any real numbers that cause my denominator to be equal to 0? The answer is
No.
no. So in other words, this function will be defined for all real numbers. There is no real number you could put in for x, such as when you square it and add 2, that this denominator would ever be 0. So this function is going to be defined for any real number. So the domain of this function, ladies and gentlemen, is all real numbers from negative to positive infinity. That's its domain. It's defined for all real numbers. Never will your denominator ever be equal to 0 for any value of x. Never. Gotta make sense. You can't square something and get a -2. You can never square a number and get -2. So this will never be -2. So the denominator will never be 0. Okay. All right, that one good. How about this one here? What would be the domain of this function, p of x, which is x plus 6 over x squared minus 2? What would be the domain of this function? Well, we got to make sure the denominator never becomes what? 0. So let's set the denominator equal to 0. Solve for x squared by adding 2 to both sides. Take the square root of both sides. And we get x is equal to plus or minus the square root of 2. And so hence, ladies and gentlemen, the only time this function is going to be undefined is if x is equal to positive square root of 2 or negative square root of 2. Therefore, x better never be equal to positive square root of 2, or x better never be equal to negative square root of 2. These values must be excluded from the domain. Interval notationally, how would we represent this domain then? Well, you might want to graph the domain first. The domain consists of all real numbers that are less than negative square root of 2, all real numbers that are greater than but less than square root of 2, and all real numbers that are strictly greater than the square root of 2. Just so long as we cannot have negative or positive square root of 2 in our domain. So the interval notational way of representing this domain formally would be from negative infinity up to the negative square root of 2, but not including that value, in union with not including the square root of -2 up to positive square root of 2, but not including positive square root of 2, in union with not including positive square root of 2 up to positive infinity. This, ladies and gentlemen, would be the formal way of representing the domain of this rational function. This is saying all real numbers except negative or positive square root of 2. Okay. Finally, let's see how much more we got here. Wow. Yeah. We're just running shy of time as usual. G of x, ladies and gentlemen, what would be the domain of this function here? And it is a function. Without graphing this, we can determine the domain, because we know that in order to have a real number, your quantity underneath your square root has to be always non-negative. As soon as your quantity underneath the square root is negative, then we no longer have a real number and our function is not defined. And so in order for us to choose a value from our domain, that value better always have this x plus 9 being greater than or equal to 0. Because if x plus 9 is less than 0, that means we're taking the square root of a negative number, which means it's no longer a real number, which means our function is undefined. So therefore, x had better be greater than or equal to 9. So our domain for this function is including 9 up to positive what? Positive infinity. That would be the domain of this function. You better not put anything into this function that's less than 9. If you do, ladies and gentlemen, if you put anything in this function, wait a minute, this should be greater than or equal to what? -9, shouldn't it? My bad, -9. You better not put anything in this function that's less than -9. If you do, then this function's undefined. So if you evaluate this function at -10, this thing is what? Undefined, because that's called an imaginary or complex number. So that would be the domain of this function here. Questions on that? Okay. Okay. Now, you can always graph those functions if you want, ladies and gentlemen, to determine their domains, if you're having a hard time determining it from the equation. All right. One last problem I want to look at here is problem 190, on page 190, excuse me. On page 190, example number 10. They give us the graph of a function here in blue. And they want us to answer all these questions here, ladies and gentlemen. All these questions here for this graph. A, what would f of 2 be? If this function in blue is the graph of a function f of x, what would f of 2 be equal to? Anybody? F of 2. What are we putting into this function? What's the input? 2 is the input.
2x.
2 is the input. It comes from the x-axis, correct?
Yeah.
So if you go to the x-axis to 2, okay, you put 2 into this function. Now we go up from the x-axis at 2. Do we hit a point on the graph? We hit the
5.
point up here. What's the y-coordinate of that point?
5.
5. So ladies and gentlemen, if you put 2 into this function, you get out a y value of 5. Hence, f of 2 is equal to 5. Your answer is 5 for that problem there. You might want to jot these down. This is example 10 on page 190. Just jot these down. A is 5. What's f of negative 5? If I put negative 5 into this function, if I go out on the x-axis to negative 5, I have to go down to strike a point on the graph. Ladies and gentlemen, f of negative 5, does it have a point on the graph?
Yes.
No.
It does not.
It
No.
does not. This is an open circle here. That means this
Oh, okay.
point,
Right.
negative 5, negative 3 does not lie on the graph. So therefore, if you try to put negative 5 into this function, since there's no point on the graph that has negative 5 for its x coordinate, we would say this is undefined. F of negative 5 is undefined for this function because there's no point on the graph that has negative 5 for its x coordinate. That's an open circle. If that was a closed circle, then f of negative 5 would be equal to what? Negative 3. You agree? Okay. Now C, find all x values for which f of x is equal to 0. Now, ladies and gentlemen, they're turning the tables on us. Now they want the y coordinate of our point to be equal to 0, and they want us to find what the x coordinate would have to be. So if the y coordinate is supposed to be equal to 0, that means we would be what? We would have to go through the y-axis at the 0th tick mark. Now, project it to the left and we hit what point? If
Negative
y is
4.
0, we hit what point?
Negative 4.
Negative 4. So if x is negative 4, y would be 0, or f of x would be 0. In other words, f of negative 4 is 0. What's another value of x such that y would be 0?
4.
Positive 4. So f of 4 would also be equal to 0. So your answers for C are x equal to negative and positive 4. D, find all values of x for which f of x is equal to 3. Ladies and gentlemen, we got to go up on the y-axis at 3 because f of x is another name for y, remember? So what x values have a y coordinate of 3 for this function? Well, now it's a continual swath here. Do you agree? It's an interval. So it looks like for x values that are greater than or equal to negative 3 up to what? But less than or equal to what? 1, correct?
1.
So therefore, it looks like the x values would range from negative 3 up to 1. So interval notationally, your answer would be open bracket, negative 3, comma, up to 1, closed bracket. So your answer for D is, what's your answer for D, ladies and gentlemen? Right here. The solutions are right below this graph, by the way. I'm sorry, if you're not getting these solutions, they're right below the graph anyways, for example 10. What's the x-intercepts, ladies and gentlemen? E, what's the x-intercepts? X-intercepts, negative 4 and 4. What's the y-intercept? 3.
3.
What's the domain of this function? The domain, x ranges from what to what?
Negative 4 to 4. Oh,
Well, negative 5, but not
5.
including negative 5 up to positive what?
Infinity.
Infinity, because this graph goes not only down forever, but also to the right forever. So the domain is from negative 5 to infinity, not including negative 5. Finally, what would be the range? What's the lowest value in the range since this graph goes down forever?
Negative infinity.
Negative infinity up to what's the largest y coordinate for any point on the graph?
5.
Positive 5. So the range is from negative infinity up to 5 and including 5. There it is. H. Open parenthesis, negative infinity, comma 5, closed bracket. Is that making sense for that problem there?
Yes.
Okay. All right. Unfortunately, we're out of time. And I mean, I wish we had more time, but we just don't have more time and we're out. I exhausted the time, ladies and gentlemen. So I'm not going to give you any classwork problem. Well, let's see here. No, I'm not going to give you any classwork problems for today. So I will update the homework, both textbook and, from Alex. And by the way, the first quiz is due by what? Midnight tonight. Do you agree?
Yes.
All right. So hopefully you've had a chance to maybe look at that, or if you haven't, you might want to get started on that. It is due by midnight on Alex, ladies and gentlemen. That quiz is done on Alex. Quiz number 1, chapter 1. Okay. All right. So I'll let you go. Have a great day. Any other questions? I'll hang on the line.
Do we,
Yep, go
do
ahead.
we need to email you our like scratch sheet for the quiz?
No, you do not.
Okay.
No, you do not. Any other questions?
I did the quiz already, and I had one answer that I oversimplified, I guess. And I was wondering if I could get half credit for it, because I did
Yeah.
have the correct answer, but it
All
was
right.
just oversimplified.
You remember what problem that was?
I do not, but I remember it was using the quadratic formula. And basically I got to a point where it was like x equals like negative b, like plus or minus square root of, but
Okay.
then I got down to the square root part, and then I just moved on from there, and I simplified it down into just like the fractions, I guess,
Mhm.
or not the fractions. I simplified it down to decimal points with my calculator
Okay.
instead of just leaving it there.
All right. If that ever happens again, just try to note the question, okay, and indicate to me what the question is. All right.
Okay.
All right. So that was one problem then.
Yeah.
Okay. What's your last name?
Porret, Porrett.
Okay. All right. I will make note of that. All righty. Plus
Thank you.
1. Okay. All right. Any other questions? Any other questions or concerns, ladies and gentlemen? All right. Well, have a good day. All right. Any other questions, Gavin, Elizabeth, or Tony? Any other questions? All right. I'm going to sign off now if there's no other questions. Okay, have a good day. Any other questions, Tony? All right.